So this is really just more that high level. What are we doing? Why are we doing it? And if we're not doing it, what should we be doing? So that's what this is about. So how do we develop software for the cloud? And is that different than how maybe some people are used to developing software or how we may have done it in the past? A lot of these practices have evolved quite a bit in the last several years, especially, but they've been evolving for a long time. So, in case you get bored along the way, here's the short answer. It's all about zombies. Zombies really are the answer for everything that people have been doing wrong and how we can evolve for the future. I'm going to come back to this, but you can just hold on to that thought. Okay, so what's the problems? What are the expectations that we're trying to address here? So people are accessing services and applications on the cloud, and there's very high expectations that come with that. They expect the services to be available pretty much all the time. They don't expect downtime. You know, think about it. If you're using Google or iCloud or Facebook, right, you expect those services to work. And if they don't, you get frustrated and annoyed, and you might keep coming back to them because you're so entwined with them. But if you're not that entwined with them, you might choose a competitor. And so expectations are super high. Security's been a big topic for a long time, and it makes the news every now and then, right? We all hear of these security holes that get discovered, and we measure how long does it take someone to fix it, right? Apple is a recent example where they actually have had a number of issues lately around security. Mac OS, I think it was in January, they had an issue and they addressed it very quickly. It was within a day. Can everyone respond that quickly? And people also own cloud. We have a lot of services there that we leverage in our development practices, and we expect those services to be available. We expect them to be easily to integrate, and we expect them to have a focus. We want to know what they do, and we want to know how to use them. So we have a lot of high expectations. So I want to talk about some situations that have occurred in my career. I've created some fictional scenarios around these, but each of these situations I've encountered in my career, and I imagine most of us have. And if you haven't, maybe you can at least imagine these situations. The first one's memory leaks. So I've built a lot of software where we've had to spend a lot of time figuring out where the memory leaks are and order to keep the application running, right? So we talked about we want to have uptime, we want to have availability. If you have a memory leak, your application eventually is going to crash because it's going to reach the limits of its memory and it will core dump. And then what do? Well, this team, what they did is they wrote a script so that they could monitor to see if the service is alive, and if it crashed, they would just restart it. However, they have a huge application and it takes 5 minutes to start. And so even if they're able to restart it, their users are going to be frustrated. And in this case, their users are using treebagel.com. They're going to go order their lunch somewhere else because the site's down. And it's down at lunchtime, right? Second situation, we refer to this in the Windows world as DLL hell. But we have this same situation really in a lot of situations. It's not just Windows development. Java has this problem. Java tries to get around this with class loading, but with varying results. And not everybody used distinct class loaders either. But you typically have this situation when you're building large monolithic software where people are using the same library, right? You have the same logging library, or you have the same whatever library. And in this case, you've got the whole product team using that same library, and you've got one component that wants to switch that out because they need the new version so they can take advantage of this cool new feature. Yet if they swap it out, it's going to affect the entire product team. And now you've got people complaining because they say, well, that's going to take me 2 weeks of effort in order to replace or in order to upgrade for that new library. And so they say, no, we can't do that. You just have to hold off, right? Next situation. I get a defect in from the field and I want to try and fix it. And so I'm making my change and I do my little local build of my component and it works just fine. So I integrate the defect and I go to do the whole build, which takes 8 hours because we're building this huge piece of software and it takes 8 hours to build. And some of you might find this hard to believe. I don't know if everyone's had this experience of an 8-hour build, but it's actually super common, and it used to be way more common than it is now. And then during the 8-hour build, it fails because, well, some other people were using the API that got changed, and it broke the rest of the build. And you might say, well, that shouldn't have happened. Like, you shouldn't make a backwards incompatible change to an API. But maybe this person didn't realize other people were using that function as an API, right? People were just calling it. It wasn't published, but people were just using it, right? And so anyway, eventually after 4 or 5 days, like the team, they get everything figured out. They finish their 8-hour build, they deploy it, they test it, they can finally do the upgrade. It takes a whole week. And then the last situation I'll talk about is just this one, reusing function. So let's say, you know, Joe wrote this application in Node.js, but I'm writing something in Python. I want to reuse what Joe wrote. Well, I can't because it's in Node and I'm in Python and they're not compatible. So I'm going to have to rewrite that, right? Other situation, I want to reuse a function, but I don't want to drag in all these other dependencies in order to use it. Or I want to use the some software application, maybe it's our rules application that provides certain capabilities, but I really don't want to pollute my computer. I don't want to spend 2 days installing that thing. These are all things that really not that long ago we had a lot of issues with. It would take us a long time just to get our environment set up, install our prerequisites, be able to call those prerequisites. We don't have to deal with that as much today because of the cloud. A lot of these capabilities are out there on the cloud and we can just call them. This is what some people are still dealing with. This is what we want to try and avoid. So these are a lot of the traditional issues around typical development practices, and people typically have built with monolithic architectures. J2EE is a really good example of this, and this leads to this type of situations when you build in this manner, right? And it's slow to start the applications. They're memory hogs. You're prone to these intertwined dependencies. They're very hard to maintain and debug. You get memory leaks, so on and so forth, right? So I come back to zombies. So what do zombies have to do with this? Zombies. So the reason this is relevant, if you think about zombies, there's tons and tons of them, right? And why are there so many zombies when you watch these zombie movies? It's because they infect each other, right? They infect people, people turn into zombies, and there's just more and more of them. And you can kill a zombie, right? You shoot it in the head and it dies, but you could still get infected and they just keep replicating. So the reason this is relevant to our situation is because I'm going to switch to Kubernetes. Kubernetes is like a key aspect to solving a lot of the issues that we want to solve. And I'm going to explain what Kubernetes is. Kubernetes is a container orchestration system. And I'll get into more detail later. But you can basically think of it, if you're not sure what it is, you can take a bunch of small Docker images and orchestrate them together so that they know how to talk to each other, and you can have a larger application that gets deployed in a very consistent manner. And when you have issues, like let's say you have a memory leak and one of your components crashes, Kubernetes is smart enough to be monitoring that and to restart it. It can tell if something is not operating at full efficiency. You basically will just shoot it in the head, going back to our zombie metaphor. If the zombie isn't behaving like you expect, you just shoot it in the head and a new one will be spawned. And that's how Kubernetes solves a lot of these problems around memory leaks, around uptime. You don't have to worry about having a single monolithic application that's running all the time. You can have sets of microservices that are running, and if one of those microservices starts to not function properly, like it's overloaded, you can spawn additional microservices to cover that performance or to deal with the fact that some of them are crashing. So it's a really powerful evolution in our ability to scale and our ability to have proper uptimes and availability and response times. Huge improvement, and we'll get a little bit more of that in a minute. I want to talk overall too, though, about it's not just Kubernetes that's going to solve this for us, right? In order to get to Kubernetes, you've got to do a lot of things up front. Microservices are key. Squads and guilds kind of evolve out of leveraging that microservices architecture. We'll talk about that. DevOps and continuous delivery are important to be able to address these things as well, because this lets us deploy fixes and features almost instantaneously within a day. You don't have to wait a week. Containers. Container, you can think of a Docker image and a Docker container when I talk about containers. And then the container orchestration, the Kubernetes. So it's orchestrating everything together. So these are the things I'm going to talk through briefly as we go through this. But once we know what we're building, how do we build it? But I'm just going to hit at a very high level. I've kind of referenced this a little bit. In the past, we've tended to create monolithic applications. And some of us may think we're not doing that today, but I see it still. And I think we need to put a renewed focus on microservices architecture and breaking things into small reusable components. And this allows us to really isolate our work, and it allows us to isolate maintenance and changes to very specific pieces of what we're building, and it allows people to reuse what we're building. The API really is the contract. So in microservices, that API is typically REST with JSON as your payload. And if you focus on that as the contract, you can really do whatever you want behind the scenes. It also allows you to decouple your language selection from the service implementation so that you can provide a service to someone and they don't have to know what it's written in. People historically have written a lot of Java code in IBM, and Java really is not the best suited language for everything we're doing. One of the things we're doing on compliance assist, a lot of the code that we're writing in the table service is more suited to Python because we're doing more data science-y type work, and we're doing natural language type work, and Python is really great at that. Java has some stuff there, but that's not where you see the majority of data scientists and ML developers doing their work. And so the other thing about Java is a lot of times it's easy to get stuck in that monolithic architecture pattern because of J2EE and all the services that are available right there within the same VM without having to go out to another microservice to get the capability. By developing microservices, it also allows squads, which I'll get into in the next section, to do their work independently and not get intertwined with managing dependencies so tightly. So I want to talk a little bit, I want to go back in time and talk about Unix. I feel like we're relearning some of the lessons that people picked up on a long time ago, but we kind of fell off the path, and we went down a path that maybe we shouldn't have gone down so far for a very long time. But if you go back to 1970s and the development of Unix, they had this philosophy. They called it the Unix philosophy, where they created very small reusable commands that you could run on a command line, and you could actually combine them together in interesting and novel ways to do different things. And pipe capability to kind of connect the output of one process to the input of another process, and redirect, being able to redirect output or redirect input was really key to making that that communication and everything function properly together. In 1978, they published and spoke about their Unix philosophy, how to write programs that do one thing and do it well. This is so analogous to microservices today. Write a microservices that focuses on one thing and do it well. And then two, write programs to work together. And in Unix, the way they did this really goes to bullet 3, write programs to handle text streams, because that's a universal interface. That's true still today. Now, we've adopted JSON in many aspects of our coding, and we use that to string applications together and allow them to talk to each other. But along the way, we made a lot of mistakes. We wrote a lot of applications that just simply couldn't talk to each other. The only way you could use them is to use their user interface, which is usually a fat client written for Windows, and you had to install Windows and install this huge application on Windows in order to get that functionality. And you could only access it through clicking with a mouse, right? So we got away from this Unix philosophy for a very long time. And it's not to say we don't need those user interfaces. It's really to say, don't mask the smaller capabilities from your user and keep them from using them. Write the user interface, but behind it, write those microservices, write those small programs that people can reuse and in a simpler way. So I really love this, and I think that there's a lot to be learned from studying history, right? It's that old saying, if you don't study history, you're doomed to repeat it. And I think that holds true. So I think it's good for us to study up on this and really look to the past and see what's still relevant today. What can we leverage? What maybe have we forgotten? We move into squads and guilds. A squad is a team, a small team. It could be 4 or 5 people typically, and they're responsible for one or more capabilities. And typically that's microservices. And each squad, each member has a unique set of skills. So you might have a user interface person, a database person, a REST person, and so forth. But that squad has all the skills they need to completely develop whatever it is they're doing in an independent manner and deploy that such that another team could then pick that up and use it. And if you think back to the Unix philosophy, this might be, a squad might be responsible for writing the cat command or the grep command or the find command. If you equate it to microservices, then a squad might write 1 or 2 or 3 different microservices depending on their kind of bandwidth. That squad, they can operate independently because of what we talked about before. They can write in their own language. They're not dependent necessarily on a J2EE framework underneath them. Hopefully they're not. They can call out to other microservices to get those functions and capabilities they need. And as long as that other microservice implements an API and they maintain some backwards compatibility, they can add new versions without removing old versions and so forth, then those squads can remain focused on their capability without being tightly coupled to those other teams. And then you also have guilds. So as I mentioned, within each squad, you've got a set of skills like a UI person, a DB person, and if you take those skill sets from each squad, you can form a guild. So a guild you could have a UI guild, a database guild, etc. And that's where those people would get together on a regular basis and discuss and learn from each other. So that way you're keeping up your expertise, you're sharing your expertise with others and so forth, and you're improving processes and how you do things. So that's the idea behind guilds. And I'll just put some references here. These are some really great videos. That Spotify video I loved. I watched it a few years ago after it had come out, and it sounded really great. I honestly didn't quite get everything they were talking about back then, but I rewatched it the other day as I was preparing for this, and everything just clicks now. So I would highly recommend that Spotify video. I think it's amazing. It really does click now as we've improved what we're doing. All right, so now we move on to DevOps and continuous delivery. So we talked about how we are going to architect things, how we're going to divvy up the work. How do we actually deliver that? So I want to talk about what makes it worthwhile to do DevOps. Why are we doing it? Are we wasting our time? Why are we being asked to write all these unit tests? Am I spending the time to write the unit test? So really the whole idea behind DevOps is being able to deliver continuously to production. And when I first heard this idea a number of years ago, I thought these people were crazy. I was like, this just cannot be done. I look at it today and I think not only can it be done, but it must be done. We're doing it because when I talked about the 8-hour build, when I talked about the build failures and how it took a week to get security patch out into the field, like you can't do that in cloud world. It's not acceptable. DevOps helps us prevent those build failures. As you all know, we're using GitHub, and it integrates and it builds and it runs our unit test, and you can almost completely erase build failures today with these practices we're using. It automates everything. It does the packaging, it does the deployment, it does unit testing, and it makes it really quick for us to make a change. But it only does that if we follow through with all the steps. So what are the basic steps? And again, most people know this. I won't spend too much time on it, but I'm going to talk briefly about the steps and the tools involved. So we all do our branch development on our local laptop, and then we're all using GitHub to do our version control, our issue management, our branch management, and as we merge our code in, it's doing builds. And it's doing those builds using a tool chain. GitHub is part of that tool chain, but also our build tool like Travis or Jenkins or the IBM Cloud Continuous Delivery is this middle aspect that's actually doing the build, it's running the unit test, it's creating the images. Once it does that, it can store those images out in Artifactory, which is hosted internally. It's a repository for NPM packages, PyPy packages, Docker images, and so on and so forth. You can store pretty much anything out there. And then once you've got it stored, another team can come reuse that as a component. They may want to pull a library into their system that they're using, or they may want to use it as a service. And if they want to use it as a service, that's where we get to this container registry. So you can also publish your Docker images out to a container registry. There is a container registry on IBM Cloud. They have both a public and a private registry. So you can make it public available to anyone, or private where you control access. And then the final step is to deploy that out to a runtime. And many of us are used to IBM Cloud Foundry and using the Cloud Foundry runtime to deploy. But a lot of people are these days moving to Kubernetes clusters as the runtime. And it's a separate stack. and there's a different way of deploying and scaling and so forth. But that's really, that's where I've been putting more effort these days. I think it's a better way to do deployment and scaling. So that's kind of like the complete flow. And I just wanted to plug unit test again. The whole thing that really makes this work is unit testing, and it requires you to do unit testing from the get-go of the project. If you've got an established project that's 3 years old and has lots of code and you didn't write unit tests along the way, yeah, you're in trouble. That's going to be hard to go back and write all those unit tests. If you're 8 weeks into your project and you haven't written any unit tests yet, you've got some work to do. It's still doable, but you've got some work to do. It's best to do this up front. You should do it day one. Before you do your pull request, you should have unit tests to go with that, and you need to run those unit tests as part of the build. And if the unit test fail, the merge fails. It won't go through, and you need to fix those unit tests before you do the final integration. So all of this is super important. If you don't do the unit test, you're not going to get that automatic deployment to production. This is the only thing that makes it work. And now there are some other tests we can do downstream, that integration testing and so forth, but it all starts with the unit test. And so if you've got people that are saying, oh, don't worry about unit testing, you need to push back. You need to go to your architect. You need to go to your manager. And you need to make sure this is sized in with your sizings and is part of your delivery. And as you're doing your Scrum, you need to show your progress on your unit testing as part of your issues. And we all have to focus on this. And this tells a little bit more about Artifactory and what you can store there. I think I've talked to that, so I'll keep going. Next big topic is containers. And again, I think most people know what containers are, but just quickly in case you don't, containers, they're really an isolation environment so that you can have a lightweight means of running typically your microservice, but whatever software you're developing, in a runtime environment that contains everything it needs to run, and it's completely isolated. And it's also something that it's agnostic to the underlying hardware or operating system that it might be running on, because it's all basically running through Linux emulation. And this has really skyrocketed our ability to deploy quickly. We used to create builds for each operating system, and those builds are very prone to failure, and they took a very long time. Docker images and Docker runtimes have really improved our ability to deploy successfully and quickly, and have just a common runtime that we don't have to deal with all different environments in debugging in Linux versus debugging in Windows and so forth. So what's a container registry? It's simply a place to store your Docker images, and Artifactory is one place to put them. As I mentioned, that's behind the IBM firewall. The IBM Cloud also has a container registry, and as I mentioned, there's private and public versions. And then there's third-party places where we can store images, such as Docker Store, Docker Hub, and so forth. Next, I'll get into packaging Helm charts. Helm charts are related to Kubernetes. Kubernetes, Helm charts are the package management aspect of Kubernetes. So they let you take multiple containers and describe, or multiple Docker images, and contain how they should talk to each other. Do they need persistent storage? What are their dependencies, and so forth. And once you create your Helm chart, it allows you to quickly deploy a whole set of containers and orchestrate them, and then use Kubernetes to scale them out. So you can see how simple it is with this command line example. You do a Helm install, and then you could get a whole host of containers that are orchestrated together with a simple command. And then you can list what's installed as well and see that it's there. Very powerful. It's so simplified installation. I can't even tell you if those of us who were, had these complex middleware solutions from 10 years ago, I mean, we would have not believed this was possible back then. So I already showed this slide, but I'm going to talk about Kubernetes again. And I'm not going to go into too much detail, but just at a high level, this thing is so powerful. It really keeps your whole systems up and running. It allows you to scale them automatically. It deals with logging in a common way, monitoring in a common way. It gives you versioning, gives you rollback. So let's say you're rolling out a new application. You can do in-place upgrades. It makes it so easy to do in-place upgrades. If you roll out an application and it doesn't roll out well, you can roll it back. You can go back to your previous version. It gives you a secure place to store credentials and API keys so that your services can communicate with each other or with external services. Gives you high availability. Gives you auto scaling. It's really amazing. This is at a very simple high level how it works. Kubernetes, you can expose your endpoints, and so then anyone connecting to your services connect to that endpoint. So that's your Kubernetes master. But behind the scenes, Kubernetes can deploy pods of your software on nodes. And you can provision one or more nodes to Kubernetes, and it can scale your application completely transparently to the end user. So you can have your CLI, a user interface, etc., connect into this one endpoint and really not even know what's happening behind the scenes. A little more complex depiction of this shows how you can use Kubernetes to scale out your application from something just really simple here on the left to something way more complex on the right. Then we also have auto scaling. This is just an example of the user interface that lets you set up auto scaling on the IBM Cloud Private. You can put in how many minimum replicas you want, what's your maximum, and what's your target CPU. This is a very simple policy. You can have more complex policies in this, but just to get the point across, it's basically going to monitor the CPU, and if the CPU exceeds a threshold, it can scale it out automatically and create a new replica set so that it can then start directing traffic to the new replica set. And this allows it to scale up and down as needed based upon the demand. So I think that is really powerful. And this is so easy to do now, and this used to be so hard to do. And most people didn't even do this. But this is the way we should be architecting and delivering things as we develop new services. And I'm going to end back where I started with the zombies. I think if you go back and look at this slide 36, hopefully you can get the analogy where, look at the far right. If one of those containers dies, who cares? I mean, we've got a whole army of zombies at our command, and they'll auto-replicate. So if one of them gets shot in the head, we still got a chance because they're just going to keep replicating themselves, and they're going to keep being a force to reckon with. So I'll end it with that.